Okay. Hello, everyone. I'm Yixian from University of Amsterdam. Today, I'll be discussing the thermal challenging in EDA. Let's start by reviewing traditional chip design flow, which comprises 5 main stages. First is the specification phase, where we design the chip's functionality and the critical constraints, such as thermal limits and power targets. Next is the RTL design, where the chip's behavior is described at an abstract level using hardware description language like Verilog. This bridges the logical functionality of the chip with its physical implementation. The system, the synthesis phase follows, where the RTL description is transformed into a gate-level netlist, serving as the blueprint of the chip at the logical gate level. After synthesis, and we move to the physical design, where gates are placed and wires are routed, and the design is optimized for timing, power, and also area. And finally, in the verification phases, we ensure the chips function as intended, meeting all the defined requirements and conditions. While this flow is effective, and it faces growing challenges as performance demands increase. The increasing number of transistors in modern chips lead to higher power consumption and heat generation. With more transistors packed into small area, power density increase, creating localized hotspots that are difficult to cool effectively. This is not only affect the performance, but also reduce the chip's reliability, as prolonged high temperature accelerate opponent degradation. Traditional method like DVFS, dynamic voltage scaling and frequency, dynamic voltage and frequency scaling, and also is typically not enough to handle this challenge, especially for the high performance design, necessitating the advanced thermal management techniques. One of the critical thermal challenge in modern chip design is the dark silicon phenomena. This occurs when only a fraction of cores on a chip can be active at a given time due to the power and the thermal constraint, while the rest must remain inactive or dark to prevent overheating. This limitation significantly reduce the chip's utilization, creating challenge in achieving maximum performance. To solve these issues, techniques like task or thread migration and advanced thermal management are often employed. Next, I will introduce examples of both an analytical method and a machine learning approach for thermal management through thread migration. We run. This is a simple example. We run 2-thread Black-Scholes workload on a 16-core system under thread rotations to prevent the thermal violation. For example, for the 2 threads were initially assigned to core 5 and core 10. Then we rotate it periodically, and the period is 500 milliseconds, and they can make the heat evenly, and we can show the trace. We can show the trace here. They can balance the temperature, and while maintaining the system performance. However, it requires extensive analysis of system characteristics, such as the cache latency and each course heat dissipation conditions, make it highly complex. Determining the rotation speed, the period involving formula sophisticated equations. While this analytic model can work well in specific scenarios, they have significant limitations. They require extensive pre-analysis of each floor plan and workload, make them inflexible for dynamic workloads or real-time adjustments. To overcome these challenges, machine learning-based approach provide a more flexible and generalizable solution for thermal management. Let's explore this by this new the machine learning-based thermal management approach. This machine learning-based approach, we start by collecting the data from the application simulations using tools like Sniper, which evaluate tasks on the various operating points, including the power budget and configurations. And then we collect the thread execution trace, such as the IPAs, the instruction per second, and cache performance data, and are extracted to create a training data set. And we use a lightweight 3 neural network to capture this relationship. Once this model is trained, and the model can predict the optimal core mapping and migration strategies during the inference time, and it can generate well, eliminating the need to exclusive pre-analyze for each floor plan. Machine learning provides a powerful and scaling solution for thermal management and make it efficiently do the heat dissipation. Thanks for your attention, and we are happy to take any questions you may have.